I tried to write this, the superscript didn't work as cleanly as I had hoped in this problem. So what we have here is y equals 2 to the x.
Okay.
What you're going to start to see here, ladies and gentlemen, we're talking about exponential growth, exponential decay, e, and then after that we start talking about logarithms. We're going to have variables as exponents now. So we have to learn how to work with them via graphs and how things change and shift and move around. So what I want to do is start by going to my calculator, and I'm going to put this in my y equals. Go to y equals 2 to the x and graph it. Hopefully everybody's kind of looks like that.
A circle.
Okay. Now, what I want to show you guys is what is exactly happening and why it has this style of a curve. Excuse me. First thing I want to do here is kind of create a real cheap table. And just for example, I'm going to say if x is 0, 1, 2, and 3. Now we're dealing with exponent rules here again. When I take 2 to the 0 power, what is anything to the 0 power? 1. It's always, always, always 1. Okay? 2 to the 0 is 1. What's 2 to the first power? 2.
2.
What's 2 squared?
4.
What's 2 cubed?
8.
All right, so far so good?
Yeah, at least.
All right. Now, think about going the other direction. What if x is negative 1? That means I have 2 to the negative 1. What is anything to the negative power?
0.
Not happy, it's some fraction. In this case, it's 1/2. What's negative 2? 1/4, very good. So it becomes 1/8. When you're dealing with these exponent rules, what we're looking at here are some of the properties when we dealt with exponents back in chapters. Yeah. What you'll notice here, as x is getting infinitely smaller and smaller and smaller and smaller, as x is approaching negative infinity, this graph, the value of y is approaching 0. It will never, ever, ever cross the y equals 0. It will never jump across that x-axis. As something, what is something called as it always approaches it, but it never touches it? What is that something called? It's an asymptote. Okay? So what is happening here is that it's approaching an asymptote. And that asymptote is at y equals 0. Okay? It's always approaching that. Yes, sir?
It was on the final, but it was related, relative.
We'll talk about that later. I still have people there to have.
Oh, yeah.
So,
Leave. Sorry.
yeah.
I apologize.
No, if you got a question about it, I'll talk to you later about it. Okay? Thank you. Now, one thing I want you to see here is that anytime we have one of these types of problems, it's just something to the x value. They're always going to have a horizontal asymptote at y equals 0. Always. Now, what's going to happen is we're going to change this up a little bit. We're going to change this into a generic form of a's and b's. I'm going to put an a in front of this b to the x now. I'm going to call this the parent function, parent growth function, call that. And this value of a will always be the y-intercept.
Oh.
Okay? It's going to always be the y-intercept. Now think about what we have here. I have y equals 2 to the x. Is there a value of a that you don't see? It's 1.
Yeah.
What's going to happen here is that we're going to not just write it as y equals 2 to the x. You're going to see it written y equals 1 times 2 to the x. Sometimes they'll write it like that. That value of a, if it's there, if it's a 4, if it's a 2, if it's a negative 6, that's always going to be your y-intercept. If you don't see it, like we did in our first example here, y equals 2 to the x, oops, that gave us our y-intercept at 1. Think about what that means here again. If you're at the y-intercept, what's your value of x? 0. 2 to the 0 power was 1. Does that make sense? Yeah. So what we do here is we have this parent function then. It's called the general form. It's going to be written as y equals a times b to the x. Not always, because what happens if I write this? Y equals 2 times 3 to the x. Where's my y-intercept now?
Oh, you got to multiply 2.
Okay.
I didn't know that was legal.
It is. So let me take a look at this quick example from what he was asking about. In this example here, I have y equals 2 times 3 to the x. I can identify rather quickly what my a's and b values are. My a value is 2. My b value is 3. If I use a generic table, yeah.
Well, why can't they just cut this like a page and they can just say A, B, and C?
This is better, literally.
Yeah, it's still.
Or the last one, 2, 3.
Okay. So again, if I'm going to go with this route, I forgot to get you guys some graphic. You guys, there's a big chunk of pile back there. It's on the top.
Pile?
Me's not talk well. Long day. Speak bad. Math fun.
I understand your vernacular.
We
Hey.
are in math.
You gonna hang out the Lincoln Inn too much?
I don't
Math, the joke that we're us at the Lincoln Inn, people are selling.
What?
I don't think anyone's
You
gonna
didn't hear about that?
My neighbors own that place, didn't I?
Wait, can you explain it? Yeah, you can explain it now.
Okay. What was it, about 2 weeks ago, there was a big drug arrest at
Oh,
Lincoln Inn.
yeah,
Because
meth
people
lab.
had a meth lab at the Lincoln Inn down.
What?
Is that a restaurant?
Longer than 2 weeks ago.
My good friends own that place.
Okay, it was long, whatever, it was a month ago, I don't know. But they found, there was 5 more people that they found, that they were looking for, that they arrested.
In the alley.
Is that when there was like a shooting or like
Yeah.
shots were fired? I don't know if someone got
Yeah,
shot.
it was an early release Wednesday, or it might have been it was the early release before parent-teachers conferences, was that one Friday. So you guys were gone by noon, and then there was a shooting at about 1 o'clock, because I remember we had an announcement here at school.
I was there.
You couldn't go south, we couldn't,
No, that was about a meth flash.
it was a meth lab, yes.
That's
I
so like
remember this.
Breaking Bad.
Wait,
No, drug deal gone bad. Let's go back to math here, guys, we got a lot to do.
Is that where the guy shot the guy's dog? Because the guy's sick, the guy's mad.
Guys, let's worry about it later, okay? Again, when I go to set these things up to graph these, when I go to graph any of these growth or decay functions, I'm always going to pick easy values to work with. I always want to start with 0. So if I'm going to use 0 for x, 2 times 3 to the 0, use your order of operations. What's 3 to the 0? 1. What's 2 times 1?
2.
So again, at 0 it becomes at 2. Then I used another one that's easy to work with. What's 3 to the first power? 3. What's 3 times 2? So at 1, it's at 6.
That means -1 is 1.
No. If it's -1, it's 2 times 3 to the -1. 3 to the -1 is 1/3.
Oh, 2 times
2/3.
2. 2/3. That's cool.
Again, in this instance here, there's nothing tacked on. It's just a times b to the x. That means I have a horizontal asymptote. It's going to be occurring at y equals 0. Oops.
So really the y-intercept is 6.
No, at 2.
But the b to the 0 or b to the 0 power
g to the 0 power is 1.
Oh.
Okay. So I have a y-intercept at 1. I have a horizontal asymptote at y equals 0. And I basically have this curve. And that's it. That's all you're going to worry about.
Oh.
You're going to plot 2 points and make a curve. Okay? When there is nothing, if it's just a, b to the x, it's always at y equals 0. Always. When there's a shift involved, then it moves. And it's very easy to find. Okay? So when we talked about shifts in the past, we had a, h's, and k's. Your h's always went with your horizontal shifts. Your k's always went with your vertical shifts. So now what we're going to do is shift it, and we're going to get this function. Y equals a times b to the x minus h plus k. Again, in this instance here, we have a horizontal shift and a vertical shift. And hopefully it looks familiar.
Looks familiar?
Remember, your h is always your horizontal,
And so it's the opposite, right? Since
Yep.
it's negative.
and your k is your vertical shift. What happens when you have a problem like this where you have a horizontal and a vertical shift? Remember when we first did horizontal and vertical shifts, I think with absolute value, we would graph the parent function as a dotted line, then we would shift it and make a solid line? We're going to do the exact same thing. We do the exact same thing with when you do the exponential growth. And tomorrow when we do exponential decay. It works the same way. We're going to graph the parent function as a dotted line, and then shift the 2 points with a solid line. So you're going to see it's going to be very, very, very easy to work with. Okay? Again, now what happens with your vertical shift? When you have a vertical shift, that means your asymptote is going to move. So if my asymptote always starts at 0, if I have a vertical shift up, my asymptote moves up. If I have a vertical shift downward, my asymptote moves down.
Yeah.
I think that's what you were asking about.
Yeah.
So now if I have something tacked on here, if I have the, let's say y equals 3 times 2 to the x minus 3 plus 4, I have now shifted that horizontal asymptote what direction? Up. How many? Not many horizontal, vertical. I've shifted that.
Good, good.
Hi, good morning. It's one of those days. That horizontal asymptote is now moved upward. Okay. You'll see. Let's look at this function.
Oh, because it's -3, so it goes up 3?
Yep. Let's copy it.
Oh, it's kind of like.
When we did these things before, do you remember how we would always label out what everything was to start with?
Yeah.
Label out what you know. You know that A
You don't know.
is 3, B is 2, H is 3, and K is 4. Remember, it's the opposite of H. So if it's X minus 3, that means it's 3. And then K is your 4, your vertical. Right? Sure.
With a K.
Now, when I go to graph this, I'm always going to graph the parent function. The parent function would be y equals 3 times 2 to the x. I graph that one first. Got it, exactly.
Didn't we just, wait, is that the same as we just did?
It might have been. I'm trying to pick numbers that are going to be very
Oh,
simple to
not
plot
same.
through.
Not same.
So if I go to plot 3 times 2 to the x, I know where my y-intercept is. If x is 0, what's your y-intercept?
3.
For the parent function. Everybody agree it's going to be at 3?
Yeah.
So it'll be at 0 and 3. I know my horizontal asymptote is here. Okay? Now, pick another easy value of x to work with. 1. What's 3 to the 1?
Wait.
Excuse me, what's, that would have been.
2.
What's 2 to the 1?
2.
What's 2 times 3?
6.
So x is 1, y is 6.
But it's x minus. So what does it be? Like 2.
I haven't done that yet. I'm graphing the parent.
Oh.
Because what I'm going to do here is after I graph the parent function, I have 2 points. I'm just going to move them left, right, up, and down, and be done with it. So this one here is a dotted line because it's not really what we're working with. Now I know that I have to move all those points horizontally, left and right, 3. And then I have to move them up 4. Move this right 3, up 4. And then that means I have to move the asymptote
Up.
up 4 as well. And now, since I'm graphing the real function, does it become solid or not? Is that solid? Again, you guys should notice that when you're graphing these types of functions, your values for your numbers for your that you choose for your x are going to be really easy. Use 1. Plot it. You're going to get a real quick answer. Move those 2 points left, right, up, and down, whatever it winds up being. Yes, sir.
Okay, so like, what if somehow it was y is greater than?
We're not doing that. We're not doing this in shaded region at all. There's no shaded
Is that
region.
like double dotted?
Yeah, no. You will see shaded region problems later on. We will talk about the intercept of conics, but that's not until April, maybe? I don't know. All right. Yes, sir.
Where did you get 1 and 6?
Well, I got the 1 and 6 in the blue. You look at the blue one here. Is that what you're talking about? 1, 6, that? This part right here? Okay. What I did here is that I chose from the parent function, I used x equals 0, then I used x equals 1. And that's what I just plugged and chugged, very simple problems to work with. The other thing that you could do, if you don't want to do this by hand as far as picking out easy problems, could you look at your table function to get you points?
Yeah.
Same idea. And then you still have, you can go from the parent function and just shift them over. Okay? So try one. Let me give you one of these.
Would we have like a non-calculator?
Yeah, this would be something that could be do with non-calculator. Absolutely. But don't worry about that. Your first quiz isn't until next week.
Come by under the.
Wait, what day next?
Wednesday.
Always the short.
We'll worry about it. Don't worry.
Always.
Okay? So, give it a second. Try to graph the parent function and then shift it. And then after that, we're going to talk about the growth and compound interest stuff. Shouldn't be that scary, I'm assuming. When I graph the parent function, it's y equals 3 times 2 to the x. I know my y-intercept is going to be at 3. And if I use 1 for x, so happens my ordered pair becomes 1, 6 again. Just try to pick numbers that I knew would fit on a graph. The parent function always has the horizontal asymptote at y equals 0. I was going to just do this to go for it. The shift tells me to do what and what to those 2 points. What direction am I going to move them?
Down and right.
I'm going to move them right
Up.
and down. Because it's -4. The k value always keeps the same sign. The h value switches. Yes, sir.
How do you know the asymptote is?
The asymptote now, basically the asymptote is going to move down 4.
So it's always to the right no matter what.
It depends on the sign. If it's -1, it's moving right. If it's +1, it's moving
The
left.
asymptote's always what k.
Yeah. Yeah.
For the parent function, is the asymptote ever not zero?
No. Yeah.
You use this formula.
You'll see it in a second. So I'm going to move this, what did I say? Right one, down 4. Right one, down 4. And move my asymptote. And just redraw it. And that's what we're looking at, ladies and gentlemen. Very simplistic stuff. Now, the other thing that you probably have used in your,
Will there ever be a vertiglass intelligence?
no.
No.
Your domain is going to be all real numbers. There's no boundary to your domain that's stopped. It can get infinitely smaller, it's going to get infinitely larger. The other part that you can use with a lot of this stuff, with exponential growth, exponential decay tomorrow, is you're going to look at growth functions. Tomorrow we'll look at decay functions. We're going to look at growth functions and compound interest today. Tomorrow we'll talk about decay functions and depreciation. So if you're looking at what's called a growth model, you have some bits and parts to it. You have this value of A, which is always your initial amount. This value of R is your rate. It's always a percent as a decimal. And this value T is your time. It's usually in years. The junk within the parentheses, that 1 plus R, they just give it a fancy name. They call it a growth factor. Tomorrow it's going to be called a decay factor because it's going to be 1 minus R. Okay? What happens here is that you are going to be given, let's say, a population. Let's say the population of DeKalb in 1990 was 25,000 people. And it had a 4% growth rate. Estimate the number of people in 2013. So what we're looking at doing here is we're going to take bits of chunks of information that you know, and you're going to substitute it into a growth model, this A times parentheses 1 plus R raised to some value of T. I know that the value of A will always be my initial quantity. How much am I starting with? It's usually population that they deal with these things. I know I'm starting with 25,000. I know my time starts at 1990. And I'm looking at the time from 1990 to 2013. How many years elapsed between the two? 23. Okay. And if I'm writing it 4%, what's 4% as a decimal? 0.04. Okay, good. So this information here we can put in and substitute into the growth model. I know that y equals, so 25,000 times 1 plus 0.04 to 23. Oops. A lot of times you'll see this in the middle written as 1.04 directly. So if they give you that growth factor of 1.04, you should be able to tell that it's a 4% growth. Yeah?
How come, like, in life, like, you'll have, especially like cars and stuff, you'll have a decay?
Yeah.
And then at a certain point, it'll start to get more expensive.
It's a buyer-seller market. I'll talk about decay stuff tomorrow, because I like talking about depreciation. There are certain things that have different rates and stuff like that. It's pretty cool. Yes, sir?
Don't you have to round down? You can have half a person.
You round up, round down. I would say round it at 0.5. All right, so you can type this directly into your calculator, and when you type that directly into your calculator, you should get, let's see, 25.
Yeah, but it's an average, so you round up.
round up if it's 0.5 or higher.
Yeah, you round up 0.5 or higher. So I have 61,617.88. We don't have 88% of a person here. We just round it up and say it's 61,618.
Yeah, what about the fridge over there?
What about
It's an approximation, ladies and gentlemen, is all it is. Okay? So roughly in 2013, if this was all true, I just made up those numbers, that would have been the population within the Cal.
What is it these days?
I don't know.
13% growth rate?
Okay. The other thing you use this for, which might make it more interesting, is working with compound interest. For those of you guys that have yet to take a business one, or are you finally enrolled in a business class?
I'm
All right.
in business law.
You use compound interest with bank accounts, things of those natures. If you're looking at compounding interest, again, you have A, the capital A is your total amount. P is what they call your principal, another word for your initial amount. R, again, stands for your rate. It's a total.
That's a T.
R is your rate. Again, it's going to be a percent as a decimal. The value N is going to be a little bit new. It's the number of times compounded. For example, if I say something is compounded annually, how many times is it compounded? Once a year, one time, right? If it's compounded semi-annually, how many times would it be compounded? Twice. Quarterly.
4.
Monthly.
12.
Daily.
365.
Lots of leap year.
Whatever.
Right.
We'll just say it's 365 for all intents and purposes, okay? Again, what you're going to wind up doing here is you're going to be given such values. How much money are you starting out with? What percentage are you earning your investment at? How much time you're going to be working, or how many years it's in there for, and how many times it's compounding out. How much are you going to get? Yeah.
Is T still?
T is still time. It'll be time in years. All right. So a real easy one to start with on this is, let's say that you have $1,000 to invest, and let's say you're putting it in the bank at 2.5%. All right. So your initial amount is $1,000. At 2.5%, compounded quarterly for, let's say, 25 years. You're going to leave it in there. How much will you get at the end? Again, when you write this out, you know that your initial amount, your principal, the amount that you're handing over to the bank, is that initial amount would be $1,000. Your rate is 2.5%, but we use that as a decimal, so what would that be as a decimal? 0.025, good.
Mr. Murphy,
Yes, sir.
do you add the exponents to them?
Get there. If it's compounding quarterly, what's your value of n?
4.
4. Remember, that's the number of times it compounds out. And how many years is this in for? 25. So your model for compounding interest, again, your total amount is going to be your principal times 1 plus your rate over the number of times, over times n times t.
So 100.
Yeah. You can substitute all of that directly into your calculator. If you type it in exactly like this with your alpha zoom to create a fraction bar, it works out perfectly. Let me show you.
No, you don't multiply that root to that root.
these other things to the act. Our principal was 1,000 times the quantity, 1 plus alpha y equals, create your fraction bar. Our rate was 2.5%, so I go 0.025. The number of times it was being compounded was 4. Hit to the right to get out of your fraction, close your parentheses. Now I can do one of two things. I know it's n times t. I can write 4 times 25 if I want, or can I just write 100? It's up to you. To the 100. And hit enter. So if you left it in that bank account for 25 years, compounding quarterly, you will come out with $1,800.64, or sorry, $1,864.61.
Is that really how it works?
That's how it works.
Like if
Wait, is that what you,
25
is that what you'll make or what you'll?
That's what your amount will be at the end.
So you'll make 800.
Make that much money,
Yes.
like stealing it.
What is that like?
Kind of a crummy investment.
Is that what they really do? Like that's what exactly?
Yeah, I don't know if that's the right percentage.
25%.
What happens here is, yeah,
So 25 years.
1,000 times 1 divided by
1 plus.
1 plus.
It's a plus sign in there. I'm sorry if you can't see that there. Yeah, it's 1 plus your rate over n, all to the n times t. So what happens here is, you guys ever seen Office Space?
No.
Really?
The
Oh,
office.
you mean like a cubicle?
Oh, in the office.
The movie Office Space?
Not in this light.
What happened in, you guys have got to go see Office Space. It's a movie rented. You could probably get it on YouTube.
The one with.
Oh,
What happens here is that the scam that they ran in that movie, see how you have can you have, 5/100ths of a cent? No, what happened is in that movie, they wrote a computer program to kind of cheat the banks from all those leftover digits. And all of a sudden they had all this money and then they thought they were all going to go to jail. It's a great, great movie. Watch it, it's very funny.
Superman movie also.
Don't they just?
Yeah, I know.
Yeah.
So the bank would tell you only have 61 cents here instead of rounding up, because the bank wants to keep those percentages, those little itsy bitsy parts of the money.
Don't they do that anyway?
Kind of. So what happens, again, when you're working with compound interest versus exponential growth, you're going to notice right away which one to use. Compounding interest is going to be dealing with money. It's going to tell you how many times something is compounding out, how many times it will turn over. Whereas a growth rate will say, hey, this is just growing at a certain percentage over X amount of time. It's very easy to distinguish between the two. Same thing tomorrow when we talk about exponential decay. Exponential decay is decaying, it's going downward, if you will. The the decay for the growth function will be a decay function. It's the subtraction. You're decreasing in value. You're losing money. It's that depreciation hit. Okay? Things like that. Like you were asking earlier with cars. Certain cars depreciate faster than other cars. Certain cars will depreciate, hit a level, and then come back up. It's all cyclical. It all depends upon market and what things are happening within markets. You see that a lot. With cars and certain values of used cars tend to fluctuate and go up depending upon if there's newer models and things like that. It's pretty crazy. So let me give you a couple of these to try for tomorrow. You will find out that it's going to be relatively straightforward. The problems themselves, I kind of chunked it up. I think there's 6 problems of graphing. The second grouping of problems deal with growth models, like the population ones. In the book, it asks you to graph some of them. I don't find the need to graph growth models. It's kind of pointless because you're never going to get a good representation of what the graph's going to look like anyway. Plus, you've got the model. You can solve all your problems via the model. So that's why I said with 43 through 54, if it says to graph it, don't graph it. I think there's like 3 of them you would skip. And then the last grouping is all deal with compound interest. You are going to fly through those. Okay? Yes, sir? You're just going to skip. You'll skip over it. Because you'll see, if you look at a question, I don't have my book in front of me. If you look at one of the questions here, it'll say, oh,
We just do it on the back of our graph, so yeah.
Yeah, you have a separate sheet of graph here, all right? See, if you look here where it says identify the additional growth factor, increase the graph function. Yeah, see here it says graph the model. So basically 44, 47, 50, 53. Says right.
There's some of them that ask you to graph and just don't do it.
All right?
Like at all.
Wait, so 30 to 42 is even?
30 through 42 is just even, it's just regular graphing. If there's no shift to it, you don't have to worry about it. It is the parent function. If there is a shift, make sure you graph the parent function as well as the shift. GR.